Thank you. So the plan for today is that the two talks will be of completely different nature. So the first one is about what is sort of very well known in non-commutative Iwasawa theory in the last few years, um, and the second one is sort of about some very wild speculations which may have nothing to do with any reality. So I apologize for the second talk in advance.
Actually, I should apologize. Whatever is wild is my fault. Whatever is real,
No.
it's good.
No, it's very kind of you, but it's my fault as well. Anyway, so the first part is about sort of formulating the so last time I gave a formulation of the main conjecture through the sort of determinant gadget of Fukaya and Kato, and this time I'll sort of formulate the main conjecture of a totally real fields case using p-adical function. So this is the 5 author paper version, and I'll sort of say how the two are equivalent. So this involves some sort of a new description of K1 that appeared in Fukaya and Kato, and it's sort of in the second part or towards the end of this lecture I'll say how this new description becomes more transparent through the topological machinery of Waldhausen or Quillen. Okay, so this is version using p-adical function as it appears in the 5 author paper. So okay, so what's the setup? So let me recall the setup from last time. So F is a totally real number field. So the first part will be sort of independent of the last talk. So this is okay. F infinity is some periodically extension which contains q mu p infinity plus. So I'm adjoining all the p power roots of unity to F and then taking the maximal totally real subfield. Okay. This contains the cyclotomic ZP extension of F. Okay. Then I assume that F infinity is totally real, periodically extension of F, and I assume that it's ramified at only finitely many primes of F. So let me denote G by Galois group of F infinity over F. H is Galois group of F infinity over F cyclotomic. Gamma is Galois group of F cyclotomic over F, and this is isomorphic to ZP. And I denote sigma by sigma finite set of finite primes in F containing all primes ramifying in F infinity. Okay, so let's recall that lambda g was the Iwasawa algebra with c coefficients. So U runs over open normal subgroups of G. So I recall this set which is defined in the 5 author paper as well. So it contains all F in the Iwasawa algebra such that lambda G modulo lambda G F is a finitely generated lambda H module. Okay. So by module I always mean left unless I say otherwise. So theorem. S is multiplicatively closed. Multiplicatively closed set in lambda G does not contain any zero divisor and is a left and right OR set. So let me say what this means. So I always forget which one means which, but I'll take this notation. So okay, so for each S in S and R in lambda, so I'm explaining what left and right OR set means. There exist T1 and T2 in S and W1 and W2 in lambda G such that I think left means this, so you take W2S is equal to W1S is equal to T1 times R, so you can switch the order, and right would mean then the other way around. So S W2 is R T2. Oh, yeah. So what does this mean? So left OR implies you can localize from left, so you can take this. Right? So if you have S1 S1 inverse R1 and S inverse R, then you can, okay, now I think I got the order wrong. Then from this what you have is, yeah, I think I got the order wrong. Okay, so this implies S inverse R. So I mean, just writing formally, this is same as W2 T2 inverse. Yeah, and then I can just, yeah, so I can just take it to the other side and write it as some invert, I mean something in S inverse. So let me just, this is very confusing. Sorry, always get confused in this algebra. So what do I want? I want to write, no, I want to write this as something in T1 inverse times W1, something like. I want to write this thing, and that's why I think this was correct. Okay, so how do I get S? So I get R so this is S1 inverse T1 inverse R1 R. Sorry about this. So the condition just means that you can invert this, and then right or implies that you can do this. Okay, and then if, because S is left and right offset, so left and, so if something is both left and right or, then you these two are equal, so there is a bijection between sorry, there is a ring isomorphism between these two, and then I denote this by lambda GS. Okay, right, so I won't give a proof of this, but I'll just give one simple example. So if so we have this short exact sequence of groups from the setting we have. So if H is finite, then S can be, then S is the following set. So we have this map from lambda G to lambda gamma, and this is isomorphic, as we saw last time, to Z, and I take reduction mod P to FP. So let me call this map IH, so augmentation at the subgroup H, and then S is just equal to lambda G minus kernel of IH. Okay, so how does one see this? So sketch is, so if you take something which lies in the kernel here, then lambda G mod lambda G F, so it goes to 0 there, so there is still a map into a surjective map into this, and so so this cannot be a finitely generated ZP module. So F belongs to kernel of IH. Okay, so this implies that S is contained in lambda G minus kernel of IH. What about the other way around? So if something is not in the kernel, then so if F does not belong to kernel of IH, then in particular its image in, so image of F in ZP is not divisible by P, by which I mean the obvious thing. So it's not divisible by P, and lambda G mod lambda G F surjects onto ZP double bracket T modulo. So the let me denote by F bar the image of this. C. And the kernel of this map is obviously a finitely generated ZP module. The map is surjective and the image is finitely generated ZP module. So the thing in the middle should be a finitely generated ZP module. Okay, so this sort of finishes the sketch. I think the proof in the paper is reduced to this case, right? So that needs some work, but it's not too difficult. Okay, and then the other thing, which is sort of not really an example of S, but which I think is interesting, is sort of based on observation of Konstantin Ardakov. So if, I mean, it sort of applies in the above case. So G as above, then there exists E greater than or equal to 0 integer such that gamma to the P to the E is contained in center of G. Okay. So gamma to the P to the E is obviously, I mean, doesn't depend on this, but take this and define S prime to be lambda gamma to the P to the E minus P times. Okay, then
pick the lifting, some lifting now gamma.
Sorry?
You picked a lifting of gamma?
Yes, I have picked a lifting of gamma, I guess. Okay, let me assume that H is abelian. Okay, then sort of everything is nice. I think it works even without that, but anyway, so so I get a map from I mean this I'll use next time, so to show how to, I mean, in a proof of this conjecture in special case. I have not made the conjecture, sorry. So this is obviously it's a central set, so it's obviously a left and right OR set, and evidently it does not contain any zero divisors and so on. So this thing injects into lambda G S, and the result here is that the claim here is that this is surjective. Okay, so we don't need to localize at a big set, we just need to. So this is easy, but I won't say anything about this. Okay. Let's denote S star by union e to the n S. So just put P in there, which is a central element. Okay. So this gives you, so this gives a extension of, and then we have a localization sequence from K theory. Okay, so this goes from K1 of lambda G to K1 of lambda G S star to K0 of, so I'll say what all these, I'll recall what all these groups are, some of them we have seen last time. So we have seen K1 of a ring, which are these two groups. So this is just GLR abelianized. So recall that GLR was just union of GLNR for n equal to 1. Okay, we have seen K0, I won't recall that, and I mean these two K0s, K0 of a ring. So K0 of lambda G and lambda G S star is Grothendieck group of the category MH of G. So this is slightly different from, so let me see what is MH of G. So this is category of perfect complexes of lambda G modules which become acyclic after tensoring with lambda G S star. Okay. Yeah. And how does one define Grothendieck group? So let me recall that briefly. So K0 MH of G, which is K0 of lambda G lambda G S star, is free abelian. I mean, it's sort of, okay, I take the following. So generators is where C is an object of MH of G, and relations. So I just take the free abelian group generated by these symbols and I put the following relation. So if C1 to C3 is a short exact sequence, then I put C2 as C1 plus C3. Okay, and one more, sorry. So 0 if C is itself a set. Okay. And so let me describe what the maps are. So the maps from Ki lambda G to Ki lambda G S star are the obvious ones given by functoriality of Ki. So the only non-obvious map is this boundary map, or it's not non-obvious, but the only one which I'll describe. So okay. So how is this given? So so if A belongs to K1 of lambda G S star, then take A in some GLN lambda G S star representing A, So you can write A as B inverse C, where B and C both lie in Mn of lambda G intersected. I mean, it's an integral thing, but it's invertible in the localization. So this is obvious if S is central, if it commutes with everything, but otherwise it's sort of needs slight thought. You have to use the OR property of S. Okay. Okay, and then what's the image of this? This is the class given by, you take lambda G to the n, make C act on it, minus lambda G to the n, so they obviously become acyclic after tensor group, after localizing at S star. And yeah, with this description of so we have this, and then so it needs like checking that it's actually a exact sequence. Okay. So proposition. So this is again in the 5 author paper. K0 of lambda G is isomorphic to K0 of lambda G S star. So in particular, surjective. Okay, I won't say anything about the proof of this, but so question here is sort of what happens for K1. This is not known in general. So does this inject into this? So this will be of some interest to us later when I make some speculations. So this in general seems very hard to prove for yeah, even for sort of fairly simple groups like ZP semi-direct product ZP and so on, it's not quite yeah, it's not easy to say whether this injects or not. Okay, so once we have this algebraic machinery, we can talk about characteristic element as in classical Iwasawa theory. So let me recall the Selmer module that we had for. So this is the Pontryagin dual of this complex. So this is also equal to R gamma. So this I will use later. So something like spec OF1 over. So this uses some local global duality and stuff. So I have lambda G. So what does this mean? So this is isomorphic to lambda G as lambda G module and Galois group sort of acts by inverse. So Galois group of Q bar over Q acts on by sigma bar inverse on the right. So by sigma bar I mean, so Galois group has, oh sorry, I should have F here, right? So Q bar over F, this, and sigma goes to sigma bar. Okay, in any case, so you can forget about the second equality for the moment. It's for later. Okay, and then the conjecture is that C lies in MH of G. Means that its cohomology is killed by S star. Okay. So this is the conjecture that one needs to sort of speak about characteristic elements. So for some C which is an objective MH of G, characteristic element of C is any element of K1 of lambda G S star. So any element X of lambda G star such that of X is class of C in K0 of MHG. Okay, so it's unique up to image of K1 of lambda G. So X is unique up to image of K1 of lambda G in K1 of lambda Gs star. So this is just like the classical situation when the characteristic polynomial is unique up to a unit in the Iwasawa algebra. So what does the main conjecture say? The main conjecture says that there exists a characteristic element with correct interpolation, so called the periodical function. So what does interpolation mean here? So let L over QP be a finite extension and O equals OL, the ring of integers of L, and let rho be a continuous homomorphism from G into GL and O. Okay. So this gives a so this extends to rho from this into MN O, okay, by continuity. this gives a map which we call phi of g, sorry, phi of rho, from lambda g into MNO tensored over ZP with lambda gamma. So what is the map? You take any g, send it to rho of g tensored with g bar. Okay. But then this thing is equal to Mn lambda O of gamma. Okay. So this thing is again in the 5 of the paper. So what you can show is that phi extends to a map from lambda g s star into Mn, the field of fractions of So how does one show something like this? So you take any element in S, you have to show that it's invertible in this ring, and sort of one can so P is obviously invertible in this, so it's enough to show that this for any element in S, and it's sort of very easy to verify in the test cases that we had. The test case being that you have H, G, gamma, where H is finite. So in that case, you have an explicit description of H, and it's sort of quite easy to verify. The general proof somehow sort of is reducing to this case. Okay. So I won't say much about this. So this gives bifunctoriality, a map from this into K1 of Mn Q.
But O of gamma is simply tensor of O
O with, yeah. So it's just the Iwasawa algebra with coefficients in O. And this is isomorphic to cross.
And what is that field of fractions of lambda O gamma?
Oh, it's just the, so lambda O gamma is just power series ring, and that's the field of fractions of that. Yeah, it's just gamma. Right. So it's really a field. Now from this you can take, okay, so there is an augmentation map from lambda O gamma to O. Okay. And one can, so let P be kernel of augmentation map. So you can extend the augmentation map to this. Okay. And then define augmentation to be infinity whenever x does not belong to, so define it to be infinity for x in the field of fractions of minus lambda O gamma P. Okay, so that's like having a pole at some. So we are almost there. So this gives us a map from K1 of lambda G S star into L union this infinity, which I denote by any psi going to psi of rho. So this might seem like a slight odd notation, but classically this would be written as So you are in some sense evaluating characters at some element of the K1. So what does this say? It says that there exists a unique element zeta in K1 of lambda G S star such that the boundary map applied to this is minus of C F infinity over F and rho kappa to the R is equal to so here R is greater than or equal to 2 even integer, rho is a Artin representation, kappa is a cyclotomic character, and this is just the L value, the complex L value. L value with Euler factors at times in sigma removed. Okay. So this is the sort of formulation of main conjecture using p-adic function. Now the question is, how does it relate to the formulation that we had last time? So let me very briefly recall the formulation that we had last time. So let me call it the Fukaya-Kato formulation. So it said that, so the main conjecture was there exists an isomorphism zeta from, let me call it Z just to distinguish from there, from determinant over lambda G of 0 into determinant over the lambda G of C with correct interpolation, which I wrote down last time. So and just out of sort of interest, so what's shown in the paper of Fukaya and Kato is that there exists an isomorphism. May not be the correct one, but there is always an isomorphism like this. Since this seems not to be very well known, I'll just sketch the proof of this as it follows from, this follows from Tate's result. So here, so this is done in Fukaya and Kato explicitly. So C is just, so let's recall that C, sorry, so I'm using C for the CF infinity over F. This is just cohomology with compact support, where U, recall that U was spec OF 1 over sigma and T was the Galois module given by lambda g with this funny action, and one was just the Tate twist. So it's shown in the book of Bas that k0 of okay, so all we need to show for this, so we need to show the class of k0 in the class of C in k0 of lambda g is 0. So but k0 of lambda g is isomorphic to k0 of lambda g modulo the Jacobson radical of lambda g. So this is shown in, for instance, in Bas' book on K theory. So he shows that if lambda g is a semi-local ring, then the k0 is sort of is isomorphic to k0 of R modulo the Jacobian of R, Jacobson radical of R. Okay, so it's enough to, and then Fukaya-Kato also show that lambda gamma c u t. So now if I tensor this with modulo Jacobson over lambda g, then this is isomorphic to R gamma c u t modulo Jacobson over t. Okay, so we can change the ring. So but again lambda g modulo Jacobson radical is, so it's semi-local, it's finite, so yeah, it's tensor product in the derived sense. I should probably put this here. So this is finite product of matrix algebras over finite fields. Okay. So this k0 of lambda g is just some copies of z, because k0 of a finite field is equal to k0 of the matrix algebra. So finite field, let's say fq, is same as k0 of fq is z. So we just have to show that it's 0 in each copy. So we are reduced to sort of the case when lambda is a finite field. So I'll let this remain here. Maybe I should. Okay. So assume lambda is fq, but in this case k0 of lambda is, so from lambda g I am assuming some ring R, okay, is M, where q to the M is this is over all I, so it may have, it has only finitely many, but it may have negative things as well. So let's see if you comment. Okay, but this is 1 by result of Tate. Sorry, this was slightly messy. Anyways, coming back to our original thing. So we have this conjecture. Now, how does one derive the main conjecture with periodic L function from this conjecture? So main conjecture implies Fukaya-Kato. So it says that there exists a so you have Z, the special isomorphism between determinant of 0 and determinant of C of f infinity over f. Now what you do is you just tensor everything with lambda g s star. So yeah, let me denote this. So this is determinant now over the localizing with determinant lambda g s star with this acyclic object. But now this is canonically so this we saw last time. If something is acyclic, then there is a canonical isomorphism between this and determinant of 0. But what is the group of automorphisms of determinant 0 over some ring R? It's just k1 of R. So automorphisms determinant. So this is how we constructed the category. So the zeta belongs to k1 of lambda g star. Is the required p-adic L function. So this is one way. What about the converse? Now this is sort of where we need a new description of k1 of lambda g s star given in terms of mh of g. Okay. So I'll just define what this group is and then stop, take a break. So let k1 of so let me recall that this was the category of finitely generated projected modules over lambda g, and so this is category of perfect complexes of lambda g modules. So let me define this thing to be so it's the following abelian group. So I define the abelian group by this generators and then take the relation. So C comma A, where C is an object of mh of g and A is an isomorphism from determinant of 0 to determinant of C. Okay, then the relations. So there are three relations. So if C is acyclic, then this is 1. So the canonical one has determinant 1, and if C1 to C2 to C3 is a short exact sequence, then as we saw last time, there is a canonical map from lambda g of C2 to determinant of C1 into determinant of C3, and this gives a so this thing gives a map from determinant 0 to determinant C2, determinant of C1 inverse into determinant of C3 inverse, which is same as determinant of C2 direct sum C1 translated by 1 and then C3 translated by 1. So call this the canonical thing. So then we want C2 direct sum C1 1 direct sum C3 1, canonical is 1. And then the third relation is that C1 direct sum C2 A1 A2 is same as C1 A1 C2 A2. So here A1 is determinant 0 to determinant of C1 and A2 is determinant of 0 to determinant of C2. So I just multiply these two things, and determinant of 0 into determinant of 0 is same as determinant 0. So A1 A2 is okay. So this is the abelian group. So the next lecture I'll show that these two are this K1 is same as K1 of lambda GS, and then we'll deduce the converse and see how this description is natural when one thinks in terms of topology.